Okay, so in this video we're going to focus on two things. We're going to talk about the angular kinematics, and then we're going to take a look at energy of rotation. Okay, so the first part here with the angular kinematics, we have the goal, the key to success when we're looking at this stuff in physics is understanding that there's a direct correlation between linear and angular quantities. Okay, so you have used these are the three most common angular kinematics equations. So we're talking about change in angular velocity. So if something's rotating and its speed is changing, it has acceleration. If it has a constant angular acceleration, then these equations apply. And it's just it's just the angular version of everything you've done. None of these equations are new. You've used every single one of them before, except you're looking at linear as opposed to angular quantities. The key to this chapter is understanding what these symbols mean, so angular velocity, angular acceleration, and angular displacement, and understanding how to use it. If you can just ignore the word angular in front and just plug them into the equations, all that stuff, you'll be good. Okay, and so also that angular acceleration is equal to the change in angular velocity over time. Okay. And then the other key is, if you want to take angular anything, let me move this back down. So take angular anything, whatever it's called, and multiply by the radius, it's going to be linear anything. Okay? And vice versa, linear anything divided by the radius will be equal to angular anything. Okay, so just plug in whatever word you want: acceleration, force, momentum, not momentum. We'll talk about momentum later. Not momentum, but basically everything else. Okay, just go angular whatever times the radius gives you that linear version. Okay, so we're going to apply this right now. And I guess another challenge here is that the concept of changing rotation is pretty abstract. Okay, it's hard to visualize the angular velocity of something changing. Okay, but let's go ahead and do this question here. So we have, you're operating the rotor, which is a cylindrical ride. Spot a passenger in distress. Clearly they got sick to their stomach, and we're going to reduce their speed over 20 revolutions at a constant acceleration. Okay, and so the question is, what is the angular acceleration experience? Okay, well, we have an initial velocity of 3.4. We have a final velocity of 2.0. So already we can see the speed is decreasing. We have some angular displacement. It says 20 revolutions, which would be 20 times 2 pi to get radians. So it'd be 40 pi radians. And now we have 1, 2, 3 quantities. We want to find the fourth acceleration. So we have to now pick an equation. Well, we know that we have an equation. Sorry, this would be initial and this would be final right there. So we know that we have an equation that says omega squared equal to omega naught squared plus 2 times alpha times delta theta. Okay, so angular displacement. We plug all those values in and we solve. So we plug in these values, the 2 right here, the 3.4 right there, the 40 pi right there, and we get an angular acceleration of negative 0.03 radians per second squared. Okay, and that doesn't seem like that much. It does depend on the radius of it. We'll say the radius is well, it doesn't depend on it, but the significance of it would depend on the radius. So we'll say that it had a radius of 15 meters for the next part. Okay, so it says how much time did the decrease take? So we can use kinematics again. Maybe we could use this equation right here, omega equals omega naught plus alpha times t. So I'll have you go ahead and solve for this. How much time did that decrease take? Okay, so we get a time, if you plug into here, of about 46.7 seconds that it took to decrease. Then it says what is the linear acceleration. So then we would multiply the 15 times 0.03, and this would be the acceleration they experience at any instant. So we have some, and it's so we have some angular acceleration, and the linear acceleration would be the acceleration at some instant, okay, that they're experiencing. And so we would just take that negative 0.03 and multiply by 15. So 0.03 times 15 is going to be 0.45. So the linear acceleration would just be 0.45 meters per second squared, because we said this times the radius of 15. Okay, 15 meters. Okay, and then it says what change in centripetal acceleration was experienced. So remember that centripetal acceleration would be what they feel, or what the acceleration inward is, how their velocity is changing, and that is v squared over r. Or since v is equal to omega times r, we can say, well, omega r squared over r, which means omega squared times r, and then one of those r's will cancel with that. And so we could say, okay, so the change in what we want to find the change, so we do it before and after. So you could find the before of 3.4 squared times 15 minus the after of 2.0 squared times 15, and see where we end up. So as we work this out, and these are actually backwards, right? Because we want the final minus the initial. So we should switch those, and we'll switch those. So 173 minus 60 is like about 113.4. Should be negative 113.4 is the change in centripetal acceleration. Okay? Which is an absurd amount. Even the 173.4, what they experienced before, is an absurd amount. So clearly this is a poorly designed problem. I just made up this 15 meters. That's probably way too much. Probably a better idea would be closer to like 2 meters. So probably get you more, probably a little bit more realistic. But this is probably really fast too for the radians per second. It's probably pretty fast to rotate. Okay, so anyway, hopefully that kind of made sense from the kinematics perspective. Now we're actually going to transition into energy. Okay, and so for this one, we want to focus on the kinetic energy of rotation. So just like we can have kinetic energy for moving a straight line, we can have rotational kinetic energy too. And the way you think about it is that each point at an instant has some velocity. Each little piece of mass at some location has some velocity v, and if we add all those up, we're going to get some, if we add up all the kinetic energies of these little pieces, we're going to get some combined kinetic energy for this whole disk or wheel that's rotating. And so the way we do that is we would add up 1/2 mv squared plus 1/2 mv squared, and so on, for all the little pieces in there to get our total kinetic energy. So that would be equal to our kinetic energy of rotation. Now we can cheat a little bit here because since they're rotating, we can say that for each piece, v is equal to omega times r, which means that for each piece it's 1/2 times m times omega times r squared. We'll add all those up. When we simplify this, 1/2 m omega squared r squared. Now once we get this, we'll put this like this: 1/2 m r squared omega squared. And so something is really significant here, because if we have this thing that's rotating, this object rotating, for every little tiny little piece on this disk that's rotating, every single piece is going to have the same angular velocity because they're all rotating at the same speed, which means that when we add all these up, we have all these 1/2 m r squared omega squares that combine, and all of these can combine together, and the only thing different is these mr squareds, because all the pieces might have different radii, okay, depending how far out they are. And so really what we end up is 1/2 times all of the mr squareds added up times omega squared. Okay, and so what we do is we're going to add up all those mr squareds and put them together. We're going to put them under one term called rotational inertia. So 1/2 I omega squared, and I is our symbol for rotational inertia. Sorry, I almost drew two I's there. Okay, and this is the basically rotational equivalent of mass. So let's make a connection back to Newton's laws. According to Newton's laws, the more mass something has, the more difficult it is to accelerate. Okay, well, that's the same thing for rotation. The more rotational inertia something has, or rotational mass something has, the more difficult it is to rotate. Okay, and so essentially, if you take every little piece and add up all those mr squareds, we get a combination of how difficult it is to rotate. And so to start, rotational inertia, another name for it is moment of inertia, is going to be just represented by how difficult it is to rotate something. And if you just have a point that you're trying to rotate, so let's say that you're swinging a yo-yo around an axis, okay, then the rotational of that the rotational inertia of that yo-yo will just be mr squared. Okay, and if you have an object like this that has multiple objects on it, you'd have to add up all the mr squareds, and you're probably starting to make the connection that sometimes you might need to use some calculus to figure it out, which is true. And fortunately, we actually have a table of them that you can use instead, just because it's some of these derivations to figure out the, like for a disk, to figure out what the rotational inertia of a disk is would take some time. Okay, and so we'll in the next video we'll introduce a table on how to do that. So the other way that you'd write this, besides as like the sum of all the mr squareds, is that I is equal to the integral of r with respect to r squared dm. So we have a series of particles here at a coordinate plane, and I'm going to use this as an example to find the moment of inertia of a system of particles. And so we have two axes. So these particles, let's just say they're stationary. We can still find their moment of inertia if they're not rotating. It would be what the moment of inertia would be if they were to rotate. And so what we're going to do here is we're basically going to say, I'm going to find their moment of inertia if they were to rotate about this y-axis. Then I'm going to ask you to do it about this x-axis next. Okay, so about this y-axis, we're going to look at each of these three particles and add up their mr squareds. So for this particle, it has a mass of 7 kilograms, and its distance away from the y-axis is 1 meter. Okay, so we're going to say negative, or yeah, we'll just use 1. So 1 meter squared. Okay, for particle 3, its distance away from the y-axis is 4 meters, and so I say 10 kilograms times 4 meters squared. And finally, for particle 2, its a distance away from the y-axis is 2 meters. So we say, okay, plus 3 kilograms times 2 meters, and we'll square that. Okay, and so we simplify all this, so we get 179 kilogram meters squared, and this is basically a measurement of how difficult they would be to rotate about this axis. Now it's going to be different to rotate them about this axis, and so I'd like you to find now the rotational inertia about the x-axis. Okay, so what you'll find is that particle 2 has no moment of inertia in this direction because its radius is 0, whereas particle 7 has actually a little bit more because it's further away, or particle 1, and then particle 3 had the same amount because it was the same distance away. Okay, and then from here, if we wanted to, we could even find rotational kinetic energy, because kinetic energy is equal to 1/2 I omega squared. So let's say if I said for the x-axis, let's say we actually got it to rotate around this axis with an angular velocity of 2 radians per second, we could plug it in. We could say 1/2 times 188 kilogram meters squared times 2 radians per second squared. And when we do this, we're going to get 1/2 times, here I'll just do it real quick and then show you. Apply this on, we're going to end up with 376 joules, okay, of energy for it to be rotating about this axis at that speed. Now the one thing I want to focus on is this unit conversion here, because we have kilogram meter squared times radian squared over second squared. And the key here is that, and this is where it gets weird, but these meters represent the radii, and so they're like meters per radius, and so these radians just cancel out, and so we get kilogram meters squared per second squared, which is a joule. Okay, and so that's where the joules pop up here. Okay, and there it is. That's rotational kinetic energy. And really the big key here is this concept of rotational inertia. Okay, we're going to spend a lot of time on this, and this is something that's very important. So if you're confused about it, I recommend going back over that section of the video. I recommend looking at it in your book a little bit, because we're going to be using this basically for the next 3 chapters. Okay? Please let me know if you have questions.